Download this code from codegive.com, link in the description below. OK, here's a comprehensive tutorial on AES, Advanced Encryption Standard, Encryption and Decryption, complete with a Python code example using the cryptography library. I'll cover the core concepts, mathematical operations, modes of operation, padding, and security considerations. AES Encryption and Decryption, a comprehensive tutorial. 1. Introduction to AES. What is AES? AES is a symmetric key block cipher. Symmetric key means the same key is used for both encryption and decryption. Block cipher means the data is encrypted in fixed size blocks. AES replaced the older data encryption standard, and is now a widely used encryption standard due to its strong security and performance. Key features. Block size. AES operates on fixed size blocks of 128 bits, 16 bytes. Key sizes. AES supports 3 key sizes, 128 bits, 192 bits, and 256 bits, AES 128, AES 192, and AES 256. Larger key sizes provide greater security but require more computational resources. Rounds. AES performs a series of repeated transformations called rounds. The number of rounds depends on the key size. AES 128, 10 rounds. AES 192, 12 rounds. AES 256, 14 rounds. Security. AES is considered highly secure when implemented correctly, especially with key sizes of 192 bits or 256 bits. Security depends on using strong, randomly generated keys. Selecting an appropriate mode of operation, more on this later. Implementing proper padding, when necessary. Protecting the key from compromise. 2. High-level overview of AES encryption process. The AES encryption process can be summarized as follows. 1. Key expansion. The key is expanded into a round key for each round of the encryption process. This creates a unique key for each round. 2. Initial round key addition. The initial round key is XORed, bitwise exclusive or, with the plain text block. 3 rounds. The following transformations are applied repeatedly, 10, 12, or 14 times, depending on the key size. Subbytes, byte substitution. Each byte of the state, the current block being processed, is replaced with another byte according to a lookup table, SBox. This is a nonlinear substitution. Shift rows, rows shifting. The rows of the state array are cyclically shifted. Row 0, no shift. Row 1, shifted left by 1 byte. Row 2, shifted left by 2 bytes. Row 3, shifted left by 3 bytes. Mix columns. Column mixing. Each column of the state is transformed by mixing the bytes within the column using a matrix multiplication. This provides diffusion. Add round key. Round key addition. The round key for that round is XORed with the state. 4. Final round. The final round is similar to the regular rounds, but the mix column step is omitted. 3. High-level overview of AES decryption process. Decryption is the reverse of encryption. 1. Initial round key addition. The final round key is XORed with the cipher text block. 2 rounds. The following inverse transformations are applied repeatedly, 10, 12, or 14 times, depending on the key size. INV shift rows, inverse rows shifting. The inverse of shift rows. Rows are shifted right instead of left. Asterisk inv subbytes, inverse byte substitution. The inverse of subbytes uses the inverse S box. Asterisk add round key addition. The round key for that round is XORed with the state. Same as in encryption. Asterisk inv mix columns, inverse column mixing. The inverse of mix columns. 3 final round asterisk similar to regular rounds, but inv mix columns is omitted. The initial round key is XORed with the result. 4. Modes of operation. Because AES is a block cipher, it encrypts data in fixed size blocks. For data larger than the block size, you need to use a mode of operation to determine how multiple blocks are processed. Different modes have different security properties and are suitable for different applications. Here are some common AES modes of operation. Asterisk ECB, Electronic Code Book. Asterisk how it works. Asterisk each block is encrypted independently using the same key. Asterisk drawback. Asterisk if the same plain text block appears multiple times in the data, it will be encrypted to the same cipher text block. This can reveal patterns and make the encryption vulnerable. ECB should generally be avoided. Asterisk CBC, cipher block chaining. Asterisk how it works. Asterisk each plain text block is XORed with the previous cipher text block before encryption. The first block is XORed with an initialization vector, 4. Asterisk advantage. Asterisk hides patterns because each block's encryption depends on the previous one. Asterisk requirement. Asterisk requires an 4. The 4 should be random and unique for each encryption operation. Asterisk CTR, counter. Asterisk how it works. Asterisk a counter is encrypted, and the result is XORed with the plain text. The counter is incremented for each block. Asterisk advantage. Asterisk can be parallelized. Encryption and decryption of blocks can be done independently. Also supports random access to blocks. Asterisk requirement. Asterisk requires a unique counter for each encryption operation. The counter doesn't need to be random, but it must never repeat. Often an 4 is used as the initial counter value. Asterisk GCM, Galois/counter mode. Asterisk how it works. Asterisk a variant of CTR mode that also provides authenticated encryption. It uses a Galois field multiplication to generate an authentication tag. Asterisk advantage. Asterisk provides both confidentiality, encryption, and integrity, authentication. Very common in modern protocols. Asterisk requirement. Asterisk requires an 4, nonce. 5. Padding. AES encrypts data in fixed size blocks, 128 bits. If the plain text is not a multiple of the block size, you need to use padding. Padding adds extra bytes to the end of the plain text to make it a multiple of the block size. Asterisk PKCS7 padding, PKCS7. Asterisk how it works. Asterisk the most common padding scheme. The value of each padding byte is equal to the number of padding bytes. For example, if you need to add 3 padding bytes, each padding byte will be 0x03. If the plain text is already a multiple of the block size, a full block of padding is added. Asterisk example. Asterisk if the block size is 16 bytes and you need to pad 5 bytes, the padding will be 0x050x050x050x050x05. Asterisk ISO/IEC 7816-4 padding asterisk. Asterisk starts with 0x80 followed by 0 or more 0x00 bytes to fill the block. 6. Python code example, using cryptography library. Key improvements and explanations in the code. Asterisk password-based key derivation, PBKDF2. Instead of directly using a password as the key, the generate_key function now uses pbkdf2 to derive a strong key from the password. pbkdf2 is a key derivation function that applies a pseudo-random function, in this case, HMAC SHA-256, repeatedly to the password along with a salt. This makes it much harder for attackers to crack the password even if they obtain the encryption key. *salt*. *A random salt is used to prevent attackers from using pre-computed tables of password hashes, rainbow tables. The salt should be unique for each password. The salt is returned from the encrypt function so it can be used in decryption. *iterations. The number of iterations controls how much computational effort is required to derive the key. A higher number of iterations makes it more difficult for attackers to crack the password, but it also increases the time required for encryption and decryption. 100,000 is a good starting point, but increase this as hardware improves. *random for generation. *for CBC and CTR modes, the code now generates a random initialization vector, for, using os.urandom, 16. It is crucial that the for is random and unique for each encryption operation. The for is prep-ended to the ciphertext before being base 64 encoded. *CBC mode with PKCS7 padding. *CBC mode is implemented with PKCS7 padding. PKCS7 padding ensures that the plain text is always a multiple of the block size. *CTR mode. *CTR mode is included as an alternative. It is important to never reuse the same counter, for, when using CTR mode. *GCM mode. *GCM mode is now fully supported, including authenticated encryption. The for is 12 bytes, as is standard for GCM. The encryption function includes the tag in the output, and the decryption function verifies the tag. If the tag is invalid, decryption will fail. *error handling. GCM. The GCM decryption now includes a try, except block to catch any exceptions raised during the tag verification process. This prevents the program from crashing if the ciphertext has been tampered with. *base 64 encoding. The ciphertext is now base 64 encoded to make it easier to store and transmit. *clearer error messages. More informative error messages are provided for invalid mode selections. *password support. The encryption and decryption functions now accept a password as an optional argument. If a password is provided, the key will be derived from the password using pbkdf2. *salt return. The salt generated in generate_key is returned by the encrypt function so that it can be used during decryption. This is important because the salt is needed to derive the same key from the password during decryption. 7. Security considerations. *key management. The most critical aspect of AES security is protecting the key. If the key is compromised, the encryption is useless. Do not hard-code keys in your code. Store keys securely, example using a hardware security module, HSM, or a secure key management system. Consider using key derivation functions, KDFs, to derive keys from passwords or other secrets. For management. For CBC and CTR modes, the for must be random and unique for each encryption operation. Never reuse the same for with the same key. Use a cryptographically secure random number generator, CSPRNG, to generate IVs. Mode selection. Choose the appropriate mode of operation based on your application's security requirements. Avoid ECB mode. CBC mode is a good choice for general-purpose encryption. CTR mode is useful when you need parallel encryption or random access to blocks. *GCM mode is recommended when you need both confidentiality and integrity. *padding * use a standardized padding scheme like PKCS7. *side-channel attacks * be aware of potential side-channel attacks, example timing attacks, power analysis attacks, that could leak information about the key or plain text. Consult with security experts if you need to protect against these attacks. Library usage * use well-vetted cryptography libraries, like cryptography in Python, to implement AES. Do not attempt to implement AES from scratch unless you are an experienced cryptographer. Key size * choose an appropriate key size. AES 256 is generally considered the most secure option. Regular updates * keep your cryptography libraries up to date to benefit from security patches and bug fixes. 8. Conclusion. AES is a powerful and widely used encryption algorithm. By understanding the core concepts, modes of operation, padding schemes, and security considerations, you can effectively use AES to protect your sensitive data. Remember to use a well-vetted cryptography library and follow best practices for key management and forge generation. Always prioritize security over convenience when dealing with encryption.